Okay, we are going to work on notes for section 10 for day 1. Okay, definition of a secant. A secant is a line that intersects a circle at exactly 2 points. Every secant contains a chord of the circle. So here is a secant, and it crosses at point A and point B, and your chord would be AB. Tangent. A tangent is a line that intersects a circle at exactly 1 point. The point is called the point of tangency or point of contact. So if we were to draw this, I'm going to do my best here to only touch the circle at 1 point, and then this would be the point where it touches, and that's the tangent. Tangent segment. A tangent segment is the part of the tangent between the point of contact and the point outside the circle. To draw this, we would go from the point that it touches the circle to another point outside. So we'd have a point here and the point of contact, and this would be the tangent segment. We can label this point P and point T. Secant segment. A secant segment is the part of the secant line that joins a point outside the circle to the farther intersection point of the secant and the circle. So to draw this, let's start outside the circle at a point, and we'll go through the circle to the farther intersection point. We can label this point P. Right here where it crosses the circle is G, and then over here will be R. So we can say that PR is the secant segment, PG is the external part of the secant segment. The external part of the secant segment. Next page. Tangent circles. Tangent circles are circles that intersect each other at exactly 1 point. We're going to have 2 types of tangent circles. We have externally tangent circles. So the external ones are right here, and you see that they only touch at 1 point. So their 2 circles are externally tangent if each of the tangent circles lies outside the other. Then internally tangent circles are going to be 2 circles are internally tangent if one of the tangent circles lies inside the other. So as you can see, we have 2 circles touching only at 1 point, and one is inside the other circle, so internally tangent. Next, we have common tangent. A common tangent is a line tangent to 2 circles. And again, we have 2 types. We have internal and external. So the common internal tangent is a tangent that's going to lie in between the 2 circles. So let me see how well I can do this. So it's a little tricky, but you want to get a line that is touching both of the circles. The line has to be in between the 2 circles, and you want it to be tangent, so really try to get it to only touch at 1 point. So that is a common internal tangent. A common external tangent is a little bit easier to draw. It is a tangent that is not between the 2 circles. So here we go. That would be your common external tangent. We have a couple postulates here. The first one says, a tangent line is perpendicular to the radius drawn at the point of contact. So if we have a tangent, if we're going to go from the center to the tangent line will be perpendicular to the radius. drawn at the point of contact. The next postulate says that if a line is perpendicular to the radius at its outer endpoint, then it is tangent to the circle. So if we know that this line is perpendicular to the radius, so this line is perpendicular to the radius, then it is the tangent. All right. The theorem 85. If two tangent segments are drawn to a circle from an external point, then those segments are congruent. So let's get that external point situated right here, and we're going to draw two tangents from that point. So let's label these. We'll have point P here. It'll touch here at X, and it'll touch here at Y. These would be the tangent segments. So another tangent segment, okay? If two tangent segments are drawn to a circle from one exterior point, then those segments are congruent. So we can say that PX is congruent to PY. Okay, common tangent procedures. You're going to want to listen to these directions pretty closely so that you understand the procedures on how to answer these types of problems. First, let's deal with a common internal tangent. So if we are going to follow the steps, step 1 says draw the segment joining the centers. So let's join the center of the circles. Draw the radii to the points of contact. So our points of contact are going to be the points of the common internal tangent. So let's draw that. Common internal tangent. There we go. Now, number 2 said draw the radii to the points of contact. So when we draw radii, remember we want them to be perpendicular to the common internal tangent. Number 3 says through the center of the smaller circle, so our center of the smaller circle's there, draw a line that's parallel to the common tangent. So the common tangent is right there. So we're going to draw a line that is going to be parallel to that. So our line that's parallel, let me do it a little bit better, be about that. And it says, observe that this line will intersect the radius of the larger circle. You may need to extend it if necessary to form a rectangle and a right triangle. So if I extend the radius of the larger circle, that line that's parallel would intersect it. And since everything is parallel, we have all these right angles going on. Okay, and we did this because now we have two figures that we know the properties of. We have formed a rectangle here, and the rectangle is right here. We also can work with the right triangle, which is right here. So right triangle. And that's how you're going to draw the figure in order to solve internal tangent problems. Let's deal, and we're not going to do the numbers right now. We're just going to look at how to draw them. Let's look at how to draw an external tangent problem. So the procedures are the same, actually. It's just going to look different, though. We have the two centers of the circle that we're going to connect. Then we're going to draw the radii to the points of contact. So this time, the points of contact are going to be the external tangents. So let's draw those so that they are perpendicular. All right. Now, through the center of the smaller circle, we're going to draw a line that is parallel to the common tangent. So here's the common tangent. This time when we draw the line, it's actually going to be inside. And if it's parallel, there's a bunch of right angles here. This would be a right angle as well. Observe that the line intersects the radius of the larger circle. So this one, we don't have to extend it because it's intersecting right here. And we formed a rectangle. I don't need to outline it because this time they're not overlapping. We have a rectangle and we have a right triangle. And then you would use the Pythagorean theorem and the properties of a rectangle in order to solve the problem. So let's start to put some numbers to these types of problems. Okay, so we have radii of two circles are 8 and 15, and the distance between their centers is 24. We want to find the length of the external tangent segment. Okay, so again, draw a line connecting the two circle centers. And we are dealing with an external tangent. So let's draw the external tangent from here to here. Draw the radii so that they are perpendicular to the external tangent. And they told us that the radii were 8 and 15. And they also said the distance between their centers is 24. Okay. Now, we need to draw a line that is parallel to the external tangent and comes off of the smaller circle. So let's draw it. Then we say, okay, right angle, and a right triangle. So we have our rectangle and we have our right triangle. So let's put the information in that we know. If this side right here is 8, well, I'm going to make this side 8. And this absolutely is not drawn to scale, but if we know that from here to here is 15, if that part's 8, this part will be 7. Okay, well, let's figure this out. On the right triangle, so for this right triangle, and I know it's not the perfect drawing, and that's okay, we have a hypotenuse that's 24, we have a leg that's 7. Therefore, we know the other leg. Well, actually, we don't, because it's not a 7, 24, 25, because the hypotenuse is 24. We have 7 squared plus b squared equals 24 squared. So we have 49 plus b squared is equal to 24 squared, which is 576. When we subtract 49 from both sides, we have b squared is equal to 527. So b is equal to the square root of 527. This can actually, it's not prime, it can be broken down, but we end up getting 17 times 31. And those two happen to be prime, and there's no pairs. So what happens is this leg is the square root of 527. So in our figure, this is 24. I don't have to have it written twice. The leg would be the square root of 527. And since that leg of the right triangle is actually the side of the rectangle, that would be this side of the rectangle as well, because opposite sides are congruent, and that happens to be the external tangent. Number 2, let's do an internal tangent problem. So let's draw the internal tangent. So it's inside. It's off a little bit. So internal tangent just means it's the tangent, the line, tangent touching it once, line connecting the two circles, and it goes in between the two circles inside, internal. So let's draw the radii, make them perpendicular, and I should have drawn this line to the centers of the circle first, but I suppose it doesn't matter. Now remember, it doesn't matter if you're going to extend it. The directions say to extend it off the smaller triangle, and that's totally fine. So if we extend it off the smaller, not triangle, but circle, we're going to make it parallel to the common internal tangent. So let's make it parallel, and we're going to extend this radius there. Okay, that's pretty not perfect. Let's do it again. So if I have this line, we're going to make this line go there, and then a little bit better. Okay, let's put in our right triangles, or right angles. All right, the distance between the two circles having a radii of 4 and 12. So radius of 4, and then this is 12. The distance between the two circles is 34. So that means 34, and I'm going to highlight this for this distance. Okay. The radii of 4 and 12 are great, but realize that if we're going to deal with the right triangle, this 12 is from here to here, and now I have an additional 4 to add on. So for the right triangle, if you can see the right triangle, the big right triangle, this side is now going to be 12 plus 4, which is 16. The hypotenuse is 34. So if we can figure out this line, right here, that's the same congruent to the internal tangent line because the opposite sides of a rectangle are congruent. So let's figure that one out right now using the Pythagorean theorem. We have 16 squared plus our leg that's missing squared equals 34 squared. So 16 squared is going to be 256 plus b squared equals 34 squared is 1,156. We subtract 256 from both sides and you get b squared is equal to 900, which this one is a nice one. B is equal to the square root of 900, which gives you a leg of 30. Okay, so if we simplified, this would have been one of the families. Moving on, we have a length of 30 here. That is the leg of the triangle, the right triangle, which is also congruent to your common internal tangent. So the answer for the common internal tangent is 30. Two circles have radii 2 and 10, a common internal tangent of the length of 12. So this time the circles are overlapping, and that's okay. So we have a common external tangent. Let's draw it down here this time. We draw radii that are perpendicular to the tangents. All right, and one of them is 2 and one is 10. And we're going to draw from the smaller circle a line that is parallel to the common external tangent. So when we draw that line, it goes in here. So a bunch of right triangles, throw them in. If this whole side, the radius is 10, if this part is 2, then this part would be 8. I completely understand these are not drawn to scale. But let's answer these questions. We also know that the distance, it says the common external tangent is 12. So this time they told us that this common external tangent is 12. Therefore, that means this leg of the right triangle is also 12. So let's take that out. We have 8 and we have 12. And then if we divide by 4, we get 2 and 3, which is not a family. You could always do 2 squared plus 3 squared is equal to your hypotenuse squared. So you have 4 plus 9 is equal to c squared. 13 is equal to c squared. So c is equal to the square root of 13. But you have to remember that you divided by 4 to get to those smaller numbers. Therefore, you'd have to multiply by 4 to get to your final answer of 4 root 13. So your hypotenuse would be 4 root 13. And that's what I believe they're asking you to find. What is the distance of the centers of the circles? It is 4 root 13. You could have always used your 8 and 12. If you would have done 8 squared plus 12 squared equals c squared, you would have ended up with the same answer down there. What's nice is that when you use the smaller numbers, you end up with your simplified radical. So you get 208 is equal to c squared, and then c is equal to the square root of 208. And you would have to play the game of, hey, is there a perfect square that goes into there? And it happens to be 16 times 13, which simplifies to that. Okay, moving on. We have
circle A, B, and C are externally tangent to each other. So A to B is going to be 15, B to C is going to be 10, and A to C is going to be 13. So we need to find the radius of each circle. So the way that you play this game is that you plug in X somewhere, and it doesn't necessarily matter where you plug it in. So I plugged in X right here, and if the radius from here to here is X, well, the radius from here to here would also be X because it's part of the same circle. And you know what, maybe I will make these in different colors so you can see them. So that would be X and that would be X. So let's do the radius of circle B. If from A to B is 15, get rid of it right here, the radius of circle B is now going to be, so from here to here, that's going to be 15 minus X. All right, well, that radius would be the same as the radius here. So that would also be 15 minus X from here to here. And we've been told that BC is 10. So we'll get to that information in a second. I'd like to deal with the radius of circle C on the other side. So let's grab brown. So if we know that A to C is 13, this radius from here to here will be 13 minus the X we already took out from circle A. And the radius from here to here is the same, 13 minus X. And you're like, holy cow, Miss Brand, what does all this have to do with each other? Now you're going to concentrate on all of this information. Because B to C is 10, but part of BC is 15 minus X, and part of BC is 13 minus X. So let's put it all together. If we had 15 minus X plus the 13 minus X, it's supposed to equal the whole line, which is supposed to be 10. Let's see if that works. 15 and 13 is going to be 28. Negative X and negative X is going to be negative 2X. That's going to equal 10. Let's subtract the 28, and we get negative 2X is equal to negative 18. Divide by negative 2, and we get X is equal to 9. So now let's plug that in and see if it works. If we are going to say that X is equal to 9, then we're saying that the radius of circle A is going to be 9. So this is going to be 9, and this is going to be 9. That means the radius of circle B is going to be, we have 15 minus X. So 15 minus 9 is equal to 6. So that means this is going to be 6, and this is going to be 6. And then finally, the radius of circle C is going to be 13 minus 9, which is going to be 4. So it would mean this part is 4 and this part is 4. Let's see if all of this adds up. If we have 9 and 6, does that add up to the 15? And it sure does. If we have 9 and 4, does it add up to the 13? And it does. If we have 6 and 4, does it add up to the 10? And it does. So these are your answers. Okay, this problem is similar to that one, but a little bit different because we have a circle that's inscribed in a quadrilateral ABCD, so it's inside there. We know that this long line from here to here, A to B, is 15, from C to D is 12, A to D over here is 31, and we're trying to figure out this length. So I think these are another fun problem. Let's do this. From A to here, let's go from here to here. That's going to be X. Well, that would mean from here to here is equivalent. It's congruent. That would also be X. So now let's make this 31 minus X. let's do this one. And if this, I wrote 13, 31 minus x, and that's from here to here, which would mean from here to here is also 31 minus x, even though I don't know what c is, to d is. These two, and I'll write this in the same color. All right, moving on. Let's do brown. From here to here, it's going to be 15 minus x, and we'll go from here to here, same thing, 15 minus x. Okay, the last part gets a little bit tricky, but we can handle it. If this whole entire side is 12, from here to here would be 12 minus the 15 minus x. Please make sure to remember the parentheses around 15 minus x. So when you distribute that negative, you get 12 minus 15 plus x, and that's very important for this problem, negative 3 plus x. So you can write it as that, or you can write x minus 3 if you'd prefer. So if this is x minus 3, then this part is x minus 3. Now we need to figure out the length of CD. We don't know what that is. Well, let's add up what we have here. We have 31 minus x, or plus x minus 3. Well, we have negative x plus x, which means they go away, gone. So now we have 31 minus 3, which gives you an answer of 28. So that is the length of CD. That concludes your notes for section 10.4.